All right. Hello, guys. Welcome to the session. Let's quickly jump into this. I believe that you should have addressed, or you should have been addressed in the main part of the session where we have talked about this Kerala Labs, placement assured program, right? We would have talked about the different functionalities of how the program works, like what are the problem statements that you face in an interview while hiring. How is that what you're learning inside the curriculum is very outdated? How is that that particular aspect is not going to help you to get a job or something like that? So we've clearly looked at all the difficulties and challenges. Now coming to a little bit technical aspects for the particular course that you've chosen, which is VLSI using Verilog, right? So I'll be deep diving a little bit inside this VLSI. What is this domain all about? What are the latest technologies that the industry is working upon? And most importantly, how we can ensure that you are part of this Career Labs Placement Assured program. What is the signing up criteria? How is it we are able to assure a job, etc., etc. So we'll go through all these details and then we'll quickly have a 5-10 minute session on the same. Okay, let's get started. Right. Now, first of all, when you look at VLSI using Verilog, right? As the statement goes, right, VLSI is the technology, whereas Verilog is one of the software that is used, right? So what is a VLSI, right? If you have to explain this to a kid, first of all, it is lesser than the size of a thumb or even a thumb imprint, guys. Okay, much smaller than that, basically, right? So if you really break down to the nano level of what exactly VLSI all about is, there are millions of transistors. Okay, what does a transistor do is very simple. Receives an electronic signal and amplifies it, or reduces its strength, etc., and sends it across. Whereas multiple transistors are put together as logic gates. Okay, a logic gate has multiple pins, 8 pins, 16 pin, etc. Plus it has a combination of resistors, diodes to control the current, the signals, etc. And then all these things integrated together form a VLSI, a very large scale integrated circuit. You guys know about this. Okay, but what is interesting is that if you look into the process of how exactly a VLSI chip is made, right, there are multiple processes involved in it. All these technicalities right now, it will not be useful for you, but down the line you can understand it. You need to understand the chip specification, the partitioning of the chip, and then the RTL synthesis, the design, the flow planning, the place and route, the final inspection, verification, and then you push it for production, etc. But the point is that, right, if you really have to think of this manufacturing in scale, right, you cannot put this in a manual layout. Okay, for example, if you have to draw the specs of what does each and every circuit or every IC in a particular chip which consists of, what does it do exactly? If you write the specs, right, it's going to be very complex, because what, thousands and even sometimes millions of chips are integrated together. So that's why we make use of a software which kind of eases the entire job, where we do not write it something physically on a paper or a notebook something, whereas everything can be run on the software, which can be used to design the chip, fabricate the chip, at the same time test it and ensure it works perfectly in the real-time operating system, right? Now that's what a VLSI chip is exactly made of, right? If you look at what is this design process, for example, what is this Verilog, right? So that's where the entire design process in the VLSI comes. See, according to you, VLSI might be a chip which has multiple transistors, etc., etc. But then the process that goes behind the screen in terms of developing those chips is where the design process comes. So the design process is divided into two spectrums. One is you write the code, the other one is you basically test the code, right? So what you typically do there in this process is you kind of simulate the code, you synthesize the code with whatever function that particular system has, and then you simulate it at the gate level in the when it's just about to deploy, and then you actually make the IC which actually has that particular functionality. Okay, so every IC that is actually made, it is tested vigorously using this particular software before it's actually sent for production or commercial usage, right? So Verilog is in, what do I say it is an hardware description language which is used to test and simulate and the software that is used to produce the VLSI, right? Now, what is the principle, right? If you look at this entire principle, right, it is operating behind something called as a Moore's law. For example, my research team gave me what is this. I asked them what is this Moore's law. They told that, theoretically looking at it, okay, we don't know whether it might happen or not, or it might happen much more than this. We don't know. Theoretically looking at Moore's law, right? Over a period of time, let's say 20 years later, 15 years later, 5 years later, or even 100 years later, or even 2 years later, you might never know. You will actually have a chip that has the exact functionality of a human brain. Okay, because everyone believes that one of the most complex systems or designs in this universe is basically the human system. So a man himself could develop another man who is, who's artificial, who could have that level of intelligence what a human brain has. So if you look at it, right, way from the early days of centuries, way back in 1900s, right, from the way and VLSI has been developed. For example, those days it used to be an electromechanical part. Remember, they used to have some vacuum tubes, etc., etc. So that has slowly started developing over a period of years. And what has developed is not just the scale of the the ICs and stuff like that. The computation speeds are also increasing. The calculations per second. Okay, for example, let's take take the phone, guys. Phone is a best example. Okay, or let's take software, right? Software is way back in 5 years down back the line, or let's say 10 years back the line. They were very slow. For example, they used to take their own sweet time to load, etc. But today's softwares have been like super fast. For example, if I'm presenting to you this in Mac, my Mac is like always very best functional, right? So what has happened is during the course of time, the processing speed has also been slowly increasing. For example, you have Pentium 1, Pentium 2, Pentium 4, you have your i5, i3, i7, etc., etc. So theoretically looking at it, right, currently Google is using something called as quantum computing, etc., and all these things. Theoretically looking at it, at some point of time, we will touch the efficiency of the human brain, is what the law says. Okay, but what is even more interesting, where are we somewhere kind of aligning with what a human brain needs to do, is that where are we aligning there is something called as a 3D IC. Now, IC itself is a 3D design, right? Multiple transistors are put together to form a single IC. Now, the IC system which is there, right, that itself can be 3D. What do you mean by that is, for example, when you look at the traditional MCBs of the printed circuit boards, right, there is a big board, right, green color board, etc. At one place, you have the logic gates. At one place, you have the memory. At one place, you have the processor. At one place, you have the analog signals, the radio frequency, etc., etc. The different things that are kind of used, certain wires which are embedded on the PCB, and they are kind of developed. Whereas what is an interposer, right? Somewhere between 2D and 3D is where all these things were very, very closely connected. Okay, they were different places, they were very, very closely connected. But what is a full 3D IC is that the different systems, the logic, the memory, the processor, the analog, etc., the power, etc., have been integrated on the same space with the same level of powers. Okay, so that much, for example, what is happening is, if you look at every different component of a chip, right, it consumes different powers. But the point is, they've been able to give a single line of power where the vertical stacking is happening, where the chip itself is intelligent enough to take the power that's actually required and dissipate the rest of the things. So what is the advantage is very, very simple, guys. If you look at why do you actually need a 3D IC in applications, that point number one, it drastically increases the computation speed. Why? Because computation speed is also a function of how closely different elements of the chips are basically faced, and most importantly, it occupies very lesser area. I'll give an example. Best example I'll give is my own laptop, Mac. Right? You take a Windows, which is typically heavy, and today you take a Mac, which is like ultra thin. Let's imagine this pen drive. Okay, you've seen some images, right? For example, like 50 years back, they used a very huge box, a box in the size of a TV or something, right? To what is that box is actually? That box has a 25 MB RAM. Okay, memory RAM, or let's say pen drive or something. But today, a 2 GB pen drive is in the size of a memory card. It's in the size of a small chip, like let's say even in the size of a contact lens. So space is very, very important when you consider physical systems, right? Especially VLS and all these things. And most importantly, the energy efficiency is consumed is very less. Why? Because unnecessary wires and lengths of circuits and unnecessary diodes and let's say resistors are not required. So the whole power that is consumed when it is being embedded in a 3D IC is relatively less when compared to a 2D IC, right? And more packing efficiency is there, therefore less heat dissipation. The performance of the system is much more higher compared to the previous node. Now, why these certain features are actually needed is that, see, what happens when you kind of use certain 3D IC? See, 3D ICs is not just about the physicality. It is not that physically they have been embedded together. They also talk about the smartness of their computation level. Okay, so what is happening with the levels of increasing computation, right? We're able to fill in more and more data to actually compute. So what is happening is they're able to scale laptops to the largest supercomputers in the world. So what was just one simple mobile phone? Like, let's take a camera. Okay, there was a camera, there was a phone, and there are multiple aspects. Now everything has been integrated to one, right? And all these things have been integrated in a laptop. And you have a supercomputer which performs multiple calculation, and whereas a laptop could eventually evolve into a supercomputer. So what is eventually happening is we're having a congregation of all the devices put together. And that's where your 3D IC plays a very, very important role. Right. And the other way to look at it, right, how they are actually made of, how a 3D IC to a 2D IC is actually made is, the base is basically the energy power. So there's a single power source, maybe certain microvolts or whatever the power is required for that. Then there's a processor stacked on it. Then the memory, whatever data information program that needs to be stored. Then you have your ADCs, DACs, etc., and all these things. Then you have your MEMS, nano devices, other sensors. The on top layer is where you have your chemical and biosensors, because that's where your chip gets exposed to the atmosphere, or let's say the surface area, something where it actually, for example, you have a solar panel, or let's say you want a drop to detect something, etc. That's put in the top level. Okay, so that physically it is appearing to the environment that is shown there. So it might look theoretically very simple, right? For example, okay, you put all these things together, you stack it up on a plate or some energy power, then your 3D IC is done. But that's not the case, guys. Behind the screen, right, every level in which it is stacked, there are a lot of complex programming behind that. And that's what we'll be learning throughout this course. Right. It might look simple, but it's a very, very complicated process. And point number two is that, okay, now we've been talking about a lot of theory, why this 3D IC is important, what are the features, why it has advantages, how it is going to help our computation speed, etc. Let's look at actual applications. Because the point is very simple, guys. Unless you clearly know where is it you can apply whatever you're learning, all what you have learned goes into the training. Okay. So if you look at it that way, right, there is something called as a organ on a chip. There's a very famous institute called as V's Institute. So V's Institute is basically one of the subsidiary colleges of Harvard University. Everybody knows about Harvard, one of the best universities for research, management, etc., etc. So inside Harvard University, right, a subsidiary institute called as V's Institute has developed something called as an organ on a chip. Now, what do you mean by an organ on a chip? Is very, very simple, guys. For example, if you have to kind of show in an image or a visual manner, right, there are different parts of the body, right, different organs of the body. You have a brain, you have a heart, you have a liver, your gastrointestinal system, your your kidneys, your muscular system, lung, etc., etc. So many things are there, right? So what do all these body functions or organs do inside the body function? Heart pumps blood, liver pumps, the digestion juice, etc., etc. You have your brain which sends signals and systems, etc. Your lung which kinds of breathes in air and breathes out air. Your kidney which kind of provides a filtration process. So ultimately, they're doing something physically, right? But ultimately, what all these organs are doing is sending some signals within themselves. Okay, now what is the difference between a healthy heart and a very, very unhealthy heart? The pumping rate, the strength of the heart, for example, the other thing which I can talk is the energy it consumes. Your heart consumes more energy, which means your heart is naturally very, very weak. It consumes nominal amount of energy, means which is very, very functional. Similarly, for your liver, brain, kidney, etc., etc. So ultimately, right, an organ does some function. What it does is something irrelevant. Okay, everybody knows about it. But ultimately, there is some input signal or energy, and there is some output signal, and that's what these organs have been doing. Because in one day, the heart suddenly doesn't start doing, giving you digestive juice and etc., etc. It's only going to pump blood. So the function has been common throughout it, and what signals come up and down depends upon the health of the organ. Now, why I'm talking about this is very simple. What this organ chip is very simple, right? They are exactly able to simulate your organ. Okay, they're able to simulate your organ. So it is as good as, right? For example, if I look at you, I don't know what is your kidney doing now. So I have to take a scan. Scan is again momentarily. Your scan is going to tell you what are you doing, what is your liver doing at that point of time. 1 hour later, I don't know how much your liver will function. 1 hour later, if you have mental stress, your heart might function in a very different manner. So I can't be taking the scan every time. So what is an organ on a chip is very simple, guys. It is a 24/7 scan of the organs that's happening inside your body. Okay, Hemant, why do we need to do this? Why is that I'm trying to simulate an organ function outside an artificial system, let's say in a laptop or a diagnosis phase, etc. If you look at it, right, for example, let's take the current situation, COVID vaccine. Okay, so right, for you to develop a vaccine, you actually have to get tested on multiple human beings. Okay, because we don't know whether the vaccine will function or not. We don't know whether the vaccine will have side effects or not. How your vaccine is going to affect your organs, etc., etc. So we can't keep compromising a lot of human beings for this test, because we're not rats, we're human beings, right? So there's a law behind that. So this is where your organ on a chip really helps you. Why? Because you can actually simulate a human being with different organ chips. There's an organ chip for a brain, there's an organ chip for a lung, etc., etc. You can actually simulate a human being. You can test the vaccine. So you're actually replacing 10 human trials there with the help of an organ chip. So what happens when you feed the vaccine? You remember we saw in this particular thing, no? Where is that thing? Let me show you that. I told hey guys, there is something called as, here we go, 1 second. There is something called as chemical and biosensors. Remember thing? So this is basically exposure on the top. So what happens is when different sensors are placed and the vaccine is injected into the system, right? Your ICs, the 3D ICs or the organ chip are actually able to react and send signals. So it is as good as accurate as a vaccine that is actually administered in a human system versus a vaccine actually administered in a organ chip system. It gives still accurate results. So A, you're able to put very less number of patients at risk for trial. C, you can do it at scale. Why? Because if you put something on a human test, right, a human takes 3 to 4 days and you only have one set of humans. Let's say 10 people are willing to volunteer. If you want to do the next test, right, I'm not very sure how much of application it has in Corona, but diseases like Alzheimer's and cancer, it has a very, very strong application. And a lot of vaccine development, it should have a very strong application in COVID-19 vaccine. Okay. So the point is you only have 10 people, right? Your test window is going to take a lot of time. because vaccine is not just about insert something and get out. You need to have multiple test results. So what happens? 10 people, you need to do 10 tests. There is a 100 time window there. You need to do 1,000 tests. There's a much more time window there. You need to do million tests. That's it. It becomes impossible to invent vaccine. That's where your organ chip comes into the picture, because you can develop 100 organ chips. You can develop 200 organ chips. You can develop 1 million organ chips. It will still isolate the same thing, right? So actually, they're able to learn what's happening inside humans without even the human need to be present in the system. Very interesting application. For example, let me talk about something else, right? Where VLSIs really help to kind of streamline the entire process. Let's take you're viewing this in your mobile phone or a laptop, right? Now, how this system was there 100 years ago? Used to have something called as a phonography, where a song was kind of recorded in a disc tape or something. You play that physically and the noise comes. Then that started developing into a cassette player, more efficient, more number of songs. Then that came as a CD player, again much more efficient and much more number of songs. Then that came into an MP3 player where you have 100 more different songs, or you're able to immediately come forward, back, etc., etc. Then it all started storing in your phone devices, where you had much more flexibility manually. Then everything became a live stream where the entire universe was available to you. So, right, just on one single song that is available on a disk, to the ability to bring the entire universe of sounds into a particular system. That's where VLSI played a very, very important role. It looks as though these technologies have developed with something else, but it's VLSI who's playing the hero role behind all these things here. Let's remember that very, very clearly. And many other applications, for example, kitchen appliances, you take your gaming appliances, right? But off late, the gaming experience has been going up and up and up, right? Where you're really able to see something called as augmented reality and all these things, right? So, n number of applications. Your PSP always has a VLSI system into it, right? Basically. Now, that almost comes to the last part of the session. What is that? Is, hey, I understood, Hemant. I understood the complexities in these technologies. I do clearly agree for the fact that, we should really build the skills to the next notch so that we can understand what is that we need to. So we really understand what is that you need to do. What are the skills that you need to learn when you consider a career in a VLSI, right? Especially when you look at our Career Labs Placement Assured program, what are the kind of technologies that we kind of touch upon us? If you look at hardware descriptive languages, remember I told you, right? When you kind of actually program the chip and understand the architecture of the chip, you use Verilog HDL, you use C++, VHDL, and System Verilog. There are different softwares which can be used. Similarly, shell scripting languages. For example, a program that gives certain instructions to, let's say, a power instructions, or let's say a signal instructions to a particular set of, systems, right? You use Bash, Perl, Python. There are many languages that can be used. Typically, Bash and Perl is used, very famous among them. The next thing is you use basically different technologies and methodologies. For example, you have your I2C inter-integrated connected circuit, you have your UART, and you have your peripheral interfaces, etc. And you also have a universal verification methodology, you have your VMM, etc. So these are different technologies on which you kind of operate the systems and understand what this world is all about. And ultimately, software. Remember, I talked about Verilog. What are the different software that you use that? Now, let's say Xilinx, one of the mother of VLSI companies, they have an office here based in Hyderabad in India, right? You have something called the Lattice Diamonds Edition software. And of course, your old classical Linux is something which you can always use to use this as a software and an OS system for the VLSI chips that have been in production. Right. Now, let me actually show you. Now, all these skills actually looks very, very theoretical for you, right? For example, if you go to a LinkedIn profile and search a person who's actually working strongly in the VLSI domain, right? These people are not come from IIT and IITs. They've come from very, very good to average colleges apart from IIT and IIT. The point is they have built some very, very excellent skills over the period of time. Remember all the skills that I suggested, right? Verilog, System Verilog, universal verification methodology, system on a chip, and then RTL verification, etc. And that has enabled them to work in these industries for a good period of 4 to 5 years. I mean, 2 to 3 years. And then he just continues to working at this point of time. For example, companies like Broadcom, companies like Moschip, companies like Wipro, who still have VLSI applications, right? So this is an iteration case. Whatever I try to show you, whatever we're going to go through the program, or applications which actually people in the industry have at this point of time. Now, what is the last part? Okay, what is that if you're interested to know about this Career Labs Assured program? Now we have enough, I wouldn't say the entire depth of what VLSI is all about. We'll have more and more interesting session. So you look at it, right? There are different courses that are available to you at this point of time, right? For example, embedded system, IoT, VLSI, etc. But you typically think this VLSI is only meant for School of Electronics. As a computer science guy, I don't have function in that. Whereas we don't classify them like that. You might be from electronics background, You might be from computer science background. You might be even from mechanical background. You might have picked up mechatronics specialist. You are still eligible to pick up this particular course or any course for that matter. Since you showed interest in VLSI design, I'm also telling you that it doesn't really matter which department you're coming from. You're still eligible for the same level of courses. Okay. Now, placement statistics, whatever I've tried to tell you this point of time, are all data and intel which I've actually taken from my students, my own students who have got placed in excellent companies. Even during the pandemic, no, that is during the lockdown, etc., we've still been able to place students. Look at this. We have 19 students, but we have 22 offers, right? So more than a student is getting more than 1 or 2 offers at this point of time, especially even during a pandemic. Yes, there has been a consistent record of getting students placed into excellent core domain companies in specifically the domain of VLSI. Okay, name any one of the big and small VLSI companies, we always have it on the list where a student we have been able to get inside for a job, right? There's enough placement statistic to prove what I've clearly told you, right? So let us say you guys are interested on the same. Okay, you want to know further instructions. Is there any discounts that is possible? Are there any subsidies that is possible? Can I pay this in installments? Hey, how do I get started about this program? Hey, show me a past record. I want to see which of the companies are getting into, etc. I can give you all these details. But what you need to do is something very, very simple. Okay, note down this particular number. Okay, save it in your contact as, let's say, Career Labs or CLAP or something like that. Send a message which says CLAP query. CLAP stands for Career Labs Assured Placement Program. CLAPP query with your name, email, phone number, and whatever query you have. Sir, what is the price of this? How do I go about this program? What is the prerequisite? What is it I'll be learning as a part of my system? What does the curriculum contain? How is that you're assuring a placement? What are the companies that visit, etc., 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 etc. We will give you a download of all this information. You can get the same. Okay. So thank you so much, guys. Hopefully you enjoyed the session and got some very interesting intel. So what you can do right now is you can pause the screen because the video is going to end in the next few seconds. Okay. You can pause the screen, note down the details. Our team will get in touch with you shortly the moment you reach with us. Okay. Thank you so much, guys. Just pause the screen. Thank you.